Okay, so we're going to talk about IMFs, or intermolecular forces, and how they relate to Coulomb's law. Now you may ask, what is an IMF? An IMF is the attractive or repulsive force between molecules caused by charges, partial charges, and temporary charges. When I say temporary charges, it has to do with the ion-induced dipole. Coulomb's law is this long thing, which is the potential energy of two charged particles depends on the charges and on their separation. So the Q1 and the Q2 stuff. Like charges will have a positive potential energy and decreases as the particles get farther apart. Opposite charges will have a negative potential energy and become more negative as the particle gets closer together. Opposite charges attract more than like charges. The magnitude of interaction between particles also increases as the charges of the particles increase. For example, when an electron with a charge of -1 is present, it will be more attracted to a nucleus with a +2 charge versus a +1 charge. Some of you might ask, how does this exactly relate to IMFs? Well, the weaker attractive forces, as in like London dispersion, usually consist of large molecules which have large electron clouds. And these electron clouds usually have a smaller charge because they are so huge. Stronger attractive forces like ion dipole or hydrogen bonding usually have smaller electron clouds and a larger charge. For example, H2O, hydrogen is very small and oxygen is very small. So the molecules can fit together more easily and have a larger charge connected between them, which produces a stronger attractive force. So now that that is refreshed, we'll go into the certain IMFs, starting with the weakest of them all, London dispersion. London dispersion is present in all molecules, as we all should know this already, but is only significant when none of the other IMFs are present. This is when electron fluctuations occur in the electron cloud, which create an extremely weak dipole, and then causing a dipole in a non-polar molecule to occur also. And here is a picture showing this. This shows the uneven distribution of electrons in a helium atom, and it shows how it creates a dipole in this atom, which causes the London dispersion. And for examples, like I said, it's in everything, so everything is an example. Next we'll go to dipole-dipole. Dipole-dipole is present in all. The polar molecules consist of both partial negatives and partial positives, which results in the attraction of a positive end of a certain dipole in an atom to the negative end of another dipole. And our picture here shows the partial negative of a dipole attracted to the partial positive of another dipole. And next we have ion dipole, which is our strongest IMF. This occurs when an ionic compound is mixed with a polar compound. And the best example would be table salt NaCl mixed with water. NaCl is our ionic compound, obviously, and H2O is our polar molecule. And this is a diagram showing the ionic dipole bonds in between the humongous negative cloud connected to all the little positives with the water over here. Next, we'll go into ion-induced dipole, which is our temporary dipole moments. This occurs when the charge of an ion is distorted in the electron cloud of nonpolar molecules and causes a temporary dipole to occur. So here we have our normal nonpolar oxygen molecule, and then when the electron cloud is distorted, it becomes slightly more polar and causes a dipole to occur. So here's our huge negative and our positive. So then it creates a dipole so it can connect to other things, which can connect to a permanent dipole if one is nearby. Next we will go into our last one, hydrogen bonding. Hydrogen bonding, it only occurs when it is introduced with FON, our little acronym that we all are familiar with, which is fluorine, oxygen, and nitrogen. Hydrogen bonding is a superdipole-dipole force. It is a large partial positive charge. And then the FON is the large partial negative charge. And due to the size of the atoms, the molecules can get very close, which I talked about earlier, how the closer they are, the stronger the attraction, because they also have a larger charge. And this is a diagram showing the hydrogen bond. It is more of a attraction sort of thing going on between these two water molecules, the oxygen being the partial negative and the hydrogen being the partial positive. Some other examples are ammonia and water like we see here, and then hydrofluoric acid. So I hope this was a helpful review, and thank you so much for listening.